here's an image of quiz 2, problem number 1, learning standard 1x. And here the learning standard was, and I quote from the syllabus, deduce algebraic order and bounding properties of real numbers using field axioms. And so a lot of what we did in 1x is talk about lower and upper bounds, minima and maxima, and infima and suprema for sets. Right? And so the big idea was what kinds of upper and lower bounds do sets have? Sets which have upper and lower bounds which belong to the set also have minima and maxima. Sets which have upper and lower bounds that are finite will also have least upper bounds and greatest lower bounds, so in a sense the best lower and upper bounds for that set, or the tightest lower and upper bounds, sometimes analysis people will say, that are called the supremum and the infimum for that set. And so the set that I gave you on this quiz was kind of a tricky set to wrap your head around. And I know that some people, it seemed like they were understanding the concept of infimum and supremum well, but they were sort of tripping a little bit on how this set was defined. So the set was the set of all unit fractions. So it includes the number 1, it includes the rational number 1/2, 1/3, 1/4, 1/5, and so on and so on and so on. And so helpfully, this person in their response to this quiz diagrammed out the set a little bit, which I think is a great, me having a visual learning preference, this always helps me when I do stuff like this. So here's 1, here's a half, here's a third, here's a fourth, and so on and so on. So there's actually how many elements in this set? Yeah, the cardinality of S is actually infinite, right? So there's infinitely many points in this set. Another thing, too, is that I feel like some of people's confusion about S was they were treating it rather not as a set, but they were treating it kind of like a sequence, almost. Like there was an order to the elements in the set, like 1 followed by a half, followed by a third, and so forth. There will be a time and a place for thinking about this as a sequence in our course. That time is probably in about 2 weeks. But for now, we're just thinking of this set as a bucket of numbers, in particular a bucket of rational numbers. Right? And so actually quite a few people, when it came time to reason about what the minimum of S was, quite a few people reasoned as this person did. Right? That the 1 over n's, the unit fractions, as the n's get bigger and bigger, and they tend toward infinity. In other words, as we look out infinitely far into what would be a sequence, if we were to put these in order, then eventually we get numbers that look kind of like 1 over infinity. And quite a few of you wrote, well, 1 over infinity, that's another name for 0. And we think about that in calculus quite a bit. Well, infinity not being a real number, we can't do arithmetic with infinity using real number arithmetic. And for the fence that delineates the playground of our course includes only real numbers, fortunately or unfortunately. And so doing arithmetic with infinity is not something that we get to do in real analysis. So 1 over infinity equals 0 is a common shorthand left over from probably when you talked about limits in a calculus class. But for our purposes, it's kind of off the table. And yet the reasoning here, I think, is worth preserving. Right? The reasoning is that the larger that this n gets, the smaller that 1 over n gets. And not only that, this 1 over n becomes arbitrarily small. However close we want to get to 0, we can get that close to 0 using an element of this set. Or, phrased another way, for any positive number that I choose, let's call it epsilon, we can find a natural number n such that 1 over n is less than epsilon. This should sound kind of familiar. And because the 1 over n's are the elements of S, i.e., another way to say this, there exists an element 1 over n belonging to S such that 1 over n is less than epsilon. So the intuition is we can always find an element of this set as close to 0 as we choose. Right? No matter how close that we want to get to 0, we can find an element of this set which is that close to 0. Right? And so that's the reasoning that I want to preserve. Before we get any more detail into this, I like the reasoning. What about the conclusion about the minimum of the set? Is the minimum of this set 0?
No, this is not included.
Because 0 is not an element of this set. right? So that's the one thing that I will take issue with here. Minimum of S is not 0 because the minimum of a set needs to belong to the set. So what is the minimum of the set? It doesn't have a minimum. Right? And that's because no matter how small an element I choose from the set, I can always find an element which is smaller. Right? In particular, if I choose 1 over n, how do I know that I can get a smaller one? What can I choose? If I choose 1/6, then you can choose 1/7. If I choose 1/9, you can choose any 1 over n that I choose. You can pull out 1 over n plus 1 and find something smaller. Right? So minimum of the set does not exist. But again, the reasoning here is something that I want to honor, right? Because this is something that we are now going to have the tools to make more precise. The kind of reasoning that says, I want to make an argument about closeness. I want to make an argument that the distance between 0 and the elements of my set can be made arbitrarily small. Right? And so closeness, distance, these are things that, in order to make these precise, we need a way to measure. We need a way to measure distance. We need a measuring stick, essentially. We need a tool to do that. So when mathematicians think about distance, it leads them into a realm that's not necessarily geometry, although it could be geometry. Really, all it requires us to do is to develop a function that can take 2 elements of a set and tell me what's the distance between those 2 elements. Right? And that distance should be a non-negative real number. For our purposes, we're going to think of distance as never being a negative quantity. It needs to be a real number. We can't have an imaginary distance, or we can't have something else, right? So we need the distance to be a positive real number. So that's what this first of these metric axioms is telling us. Right? The distance between any 2 elements, x and y, needs to be greater than or equal to 0. That's the non-negativity property. The other thing that we need distance to do is we need distance to also be able to tell us when 2 elements are in fact the same element. What should the distance between one element and itself be? 0. And so that's the second of our metric axioms, right? That the distance between any element of it and itself is always 0, but then furthermore, the converse is also true. That if I have 2 elements and I can show that the distance between them is 0, then I can conclude that those 2 elements are the same element. Right? So it needs to go both directions. The distance between anything and itself is 0, and whenever the distance between 2 things is 0, those 2 things must have been the same. That's the second axiom called the non-degeneracy axiom. dxy is equal to 0 if and only if x and y are the same. And then 2 more properties that are important in order to give us a sensible notion of distance. The third one is that it shouldn't matter if I measure the distance from A to B or whether I measure the distance from B to A, I should get the same answer. So distance shouldn't care which order I ask it about 2 same elements. Right? Distance should always give me the same answer. And so there's a symmetry requirement. That's the third of our axioms. But it's the fourth axiom that really makes this from just kind of a function into a distance function. And the inspiration behind it comes from the idea that if I have 3 elements of my set, let's call them x, y, and z, that it will always be no less distance to go directly from x to z. So that distance is what we call dxz here in this inequality. It will never take us a longer distance to go directly from x to z than it would take us in total to go from x to something else, y, and thence from y to z. Right? So we call it a triangle inequality because of this picture, that the distance from x to z can never be larger than the sum of the distance from x to another point y, followed by the distance from y to z. So this is sometimes, I think of it sometimes as a codification of that old saw, the shortest distance between 2 points is a straight line, right? This is sort of the triangle version of that straight line. If I go from x to a third point y, and then I go to z, I'm not ever going to get a shorter path than if I measure the distance directly from x to z. And so this inequality, dxz, is less than or equal to the sum of dxy plus dyz. This has to hold, here's a quantifier, for all elements x, y, z in my set. And that is an axiom that needs to be true of anything which we claim to be a sensible measurement of distance. So this set of axioms is what makes any measuring stick a legitimate measuring stick. And any function on the Cartesian product of a set with itself. In other words, it has to take one element from our set and another element from our set and produce from those two elements a real number. Anything which satisfies these four criteria we can call a distance measurement, or mathematically we call it a metric function. So metrics are a big deal in geometry for obvious reasons. But what's interesting about it is that there's not just one way to measure distance. There's not just one sensible way to set up a function which does these four things. Right? There are those that we're used to from high school geometry, like the Euclidean metric. The distance formula in the xy plane, for example, meets all these criteria. Right? But it is not the only thing which does so. So part of what you'll do in this packet is also explore some of the other weird ways of measuring distance that are out there in the world. And in fact, as they get funkier and funkier, they become less geometrically intuitive, and they become a topic in not geometry, but what we call topology. Topology is a way to kind of almost abstract the notion of closeness and distance away from needing even sometimes to be able to measure the distance between things. But when we can measure the distance between things, we give rise to what's called the metric topology. So this is again, the very beginning, the very taste of a very long string of things that we could do with metrics. So what metric do we care about in real analysis, in particular the analysis of functions of a single real variable, which is really, if you put a finer point on the description of our course, that's really what it is. It's the analysis of functions of a single variable, real valued functions of a single real variable. So the metric that it turns out that we care the most about and is the most intuitive is the metric given by the absolute value. And the whole purpose in life of the absolute value, you may recall, is to measure how far away from zero a number is on the real number line. That's one way of saying what an absolute value does. Right? Sometimes students, when first learning absolute value, just remember it as something that throws away negative signs but keeps positive signs. That's fine, right, on the real number line. But really, we care about it. Why it's important is that it measures distance. It measures the distance to zero. So, for example, here's 0 on the number line. Here's -3 or something like that. The absolute value of -3 is 3 because the distance between -3 and 0 on the number line is 3 units. Right, so absolute value is 3 because it measures how far away from 0. The cool thing about that, though, is that because the real number system is not just a norm space, but it also has a vector space property that underlies it. And that's just a fancy mathematician-y way of saying that we can also add and subtract real numbers. We can also multiply real numbers by other real numbers. So there's some additional arithmetic that is a part of the real line. And because of that arithmetic, the absolute value is not only able to measure how far numbers are away from 0, but it can also be used to measure how far numbers are away from one another. So that's what definition number 2 does for us. It just reminds us that if we take this whole picture, and let's say we shift everything to the right by 7 units or something like that. I'm just going to add 7 to everything. So -3 plus 7 is going to become 4. 0 plus 7 is going to become 7. And so now 3 here is being set up as the distance not between -3 and 0, but between 4 and 7. Well, where would this -3 come from the numbers 4 and 7, that would explain why the absolute value of -3 is equal to 3 in this picture? Where does this -3 coming from?
4 minus 7.
4 minus 7, exactly. So that's the other really awesome thing about absolute value. It's capable not just of measuring distance from 0, but measuring distance from one another, from among the points on the real line. And so that means that it's our tool anytime we want to discuss closeness to anything, closeness to any real number on the number line. And absolute value is our way to do that. And then this theorem 1.17 establishes a couple things. It not only establishes those axioms of a metric which are not obvious otherwise about absolute value. So for example, the triangle inequality. We can show directly that the absolute value function satisfies the triangle inequality. It also establishes some other facts. It establishes what's called a reverse triangle inequality down here on the bottom that doesn't that deals with the absolute value of x minus y instead of x plus y. It also establishes a property called homogeneity, which says that the absolute value of a product of two numbers is the same as the product of the absolute values of those two numbers. So that's going to give us another tool that we can use for simplifying expressions that involve absolute values in them. And then the last thing that we have up here at the top, and it's, again, a little bit obvious statement, I guess, is that the absolute value of a number and the opposite of the absolute value of a number always bracket that number. Right? So any number is always between its own absolute value and the opposite of its own absolute value. In fact, one or the other of these inequalities will always be an equal sign. Right? In fact, in the case of x equals 0, both of them will be equal signs. But again, by definition of the absolute value of x is always equal to x if x is positive. So if x is positive, this one is an equal sign. Whereas if x is negative, the absolute value of x is equal to negative x, and then in that case, this one would be an equal sign. So this theorem just establishes some properties, the most important of which are probably the triangle inequality and what we call the reverse triangle inequality in parts C and D. So the next thing we need to do is figure out, okay, if we believe all of this stuff, how is the triangle inequality going to really help us do real analysis?